Welcome to the 8.5 notes video. The first thing that we're going to do is look at remembering some of the graphs that we've talked about before. Some of these we talked about last semester. And then we're going to look at specifically graphing quadratic equations. So if we're looking at our examples here, A, B, C, D, and E, only one of these is quadratic. Specifically, only B is quadratic because it's x to the second power, and that's what we said makes something quadratic, is that its highest degree is 2. So when we're looking at these and we want to look at how to graph them, what we're looking at is the degree or the parent function of this equation. So for example, in A, we're looking at the graph of y equals x cubed. Now you can always check these on your calculator, but it'd be a good practice to start thinking about what does this look like without having to go to the calculator, because the more you can recognize these graphs, the easier it will be to graph them as we progress. So part A is a cubic function, and a cubic function looks like this. We said it's kind of like John Travolta dancing, and depending on if our coefficient is positive or negative, it could have a positive rate of change or a negative rate of change, kind of like slope, but since it's not constant, we don't call it slope. Part B, that's quadratic, and a quadratic equation has the shape of a parabola. So that's going to look like this if our coefficient is positive, or this if our coefficient is negative. And don't worry, if you're not sure what I mean by coefficient, that's one of the things that we're going to be talking about in the notes. Part C, we have y equals x, which is a line. So it's either this if I have a slope that's positive, or this if I have a slope that's negative. D, that's a square root function. Now a square root function, remember, inside of our square root, we can only have positive numbers. And so our square root function is like half of a parabola that fell over. And then we have E, which is our cube root function, and we can have any number in our cube root function. And so our cube root function has positive values, but it also has negative values. Okay, so those are kind of our basic parent graphs. We call them parent graphs because they are the general shape, but not the exact shape of our functions, right? If I had just y equals x squared, it would look like this with our vertex at the origin. This point at the bottom here is called a vertex. But usually we have something a little bit more complicated than that. So let's look at what happens when I have a quadratic function. So with a quadratic function, if we have that f of x equals ax squared plus bx plus c, so this is what makes it quadratic. It has that squared term, where f of x is y. So we said this is our y value. Y equals ax squared plus bx plus c. A, b, and c are real numbers, so we have real number coefficients, and a is not 0. So if a was 0, this would be linear. But we're saying a cannot be 0. So this whole thing is just a fancy way of saying this is quadratic. So if we have a quadratic function, if a is positive, a is my coefficient for my highest degree term. This is called the leading coefficient. Coefficient. I'm going to write that over here again. Coefficient. A little bit more legibly. If a is positive, our leading coefficient is positive, then our parabola opens upward. Positive like a smile. If our leading coefficient is negative, it's less than 0, then it opens downward, negative like a frown. So let's look at graphing some of these equations. In example 1, we're going to start by graphing x squared, and then on the same graph, we're going to compare it to the graph of x squared plus 6. So how do we graph something? Well, we need x and y values, and you can always confirm on your calculator, but you really want to try to graph these by hand first. So if I have an x value of let's pick some positive and some negative values, because notice how it curves like this. I want to make sure to get values so that I can see both sides of the curve. So let's try -2, -1, 0, 1, and 2. Okay, if we substitute this in, we would get -2 squared, which is 4. Substitute again, -1 squared, which is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. So we get these ordered pairs, -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. Notice how these y values kind of have this symmetry to them. 4, 1, 0, 1, 4. That's going to be a property of parabolas. So we go -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. There is our graph of x squared. And then we want to look at, well, what about for g of x where it's x squared plus 6? So new xy table. We'll use the same values, -2, -1, 0, 1, and 2. And then we have -2 squared, which was 4, plus 6. 4 plus 6 is 10. -1 squared, which is 1, plus 6 is 7. 0 squared is 0, plus 6 is 6. 1 squared is 1, plus 6 is 7. 2 squared is 4, plus 6 is 10. So again, notice that symmetry that we have here. So we have -2 and then up to 10. The top of the graph is 10. -1, 7, 0, 6, 1, 7, 2, 10. So what happened here? Well, if we're looking at the shape, it has a very similar and it ends up being exactly the same shape. So notice here, I would go down 3 over 1, down 3 over 1. So the distance between all of these points is exactly the same in the top graph versus the bottom graph. And this one was x squared plus 6. So what happened actually is that this graph moved 1, 2, 3, 4, 5, 6 units up. Up 6. So we took the graph of x squared and we moved it up 6. That's what this plus 6 actually does. So what do you think would happen if we had x squared minus 6? Well, if plus 6 goes up, then minus 6 would go down by 6. What I'd like you to do is do the try this and then see what graph you get. And then in the Ed Puzzle question, I'd like you to describe in words what was the movement. So like the plus 6 moved up 6, minus 6 went down 6. What is the movement of this graph? All right, next let's look at example 2. So example 2, now we're looking at the same type of thing. We're looking at a graph of x squared and a graph of a little bit more complicated of a function. This one is x minus 3 squared. Notice the minus 3 is inside of the argument, meaning the x minus 3 is being squared as a unit. Okay, the ones that we were looking at in example 1, that plus 6 was outside of the squared. It was after x had already been squared. So we're going to look at what's the difference between when the number being added is inside of the part being squared versus outside of the part being squared. So again, we're going to make our xy table. Okay, and we're going to go -2, -1, 0, 1, 2. For x squared, we've already seen these values. 4, 1, 0, 1, 4. And so we'll plot those same points, 2, 4, negative 1, 1, 0, 1, 1, 2, 4. There's my graph of x squared. And then we want to graph g of x, y. And let's start with negative 2, negative 1, 0, 1, 2. Notice I'm leaving space on my x values. You'll want to leave some space there. Okay, well, now I have negative 2 minus 3 and then squared. So order of operations says I do the negative 2 minus 3 first. So that actually gives us negative 5 squared, which is 25. That's too big to graph on our plane. So we're going to choose not to graph that point, which means we're going to need another point later on because we have to use at least 5 points. So then here we have negative 1 minus 3 squared. Negative 1 minus 3 is negative 4 squared, which is 16. Again, that's too big to graph, so we're going to choose not to graph that point on our graph here. 0 minus 3 squared is negative 3 squared, which is 9. That one would fit. So here we have 0, 9. 1 minus 3 squared is negative 2 squared, which is 4. That one we can graph. 2 minus 3 squared, 2 minus 3 is negative 1 squared, which is 1. Hey, we can graph that one. So far we have 3 points, so we need at least 2 more. 3, 4. 3 minus 3, oh, that's nice, is just 0. 4 minus 3 is 1. Squared is 1. Okay, so now we have our 5 points. And if we look at this, that looks like a different shape. However, remember this is a parabola. So it keeps going, and this keeps going. So let's see if we can find, so we would expect the point to be right here. Let's see if we can find the point. What is happening when x is 5? 5 minus 3 is 2. Squared, whoops, is 4. So that's exactly what happened. Notice our original graph of x squared and our graph of the quantity of x minus 3 squared are again the same shape. We just have an additional point plotted here. So what would happen if we went to negative 3? What would happen if we had negative 3 here? Well, negative 3 squared is 9. So what actually happens is we can see that these are indeed exactly the same shape. Exactly the same shape. However, this x minus 3 squared has been shifted 1, 2, 3 units to the right. So this went to the right by 3. So then what do you think f of x, where x plus 3 is squared, would look like? Notice here we have a minus 3, here we have a plus 3. So again, the opposite sign makes it go the opposite direction. Since this is in parentheses, it's not going to move up, it's actually going to move to the left. So that will go to the left by 3. Okay, we're going to talk about how do you know how far it moves and in which direction does it move. So this minus 3, we might say, hey, minus is to the left. So why did this move to the right? Well, we can see in our calculations that this minus 3 is actually subtracting 3 from each of our values being squared. So what actually happens is that my value, my y value, is not 3 units over. It's my x value that's 3 units over. And so the question we can ask, just like when we were finding domain, is what value would make this 0? What would make this 0? So the value that would make that 0 is x equals 3. And so we can say that we moved over to where x equals 3 to start our parabola, the point where we have our symmetry, and that point is called the vertex. So the vertex of our parabola is when x equals 3. And that's how we can kind of think about, instead of thinking of it as x minus 3, which we might be tempted to say would go to the left, if we use this question of what makes this 0, we can see that it actually moves to the right because we have an x equals positive 3. So I'd like you to think about that for a second, and then go ahead and do the try this, and then again on Edpuzzle, type in the words of what does this transformation represent? What movement has this graph gone through? Did it go up or down or right or left? And by how much? And I do want you to graph it here, and we'll talk about the graph if anyone has questions during our next class. Now let's take a look at example 3. So we saw what happens when we do transformations with addition or subtraction that's not being squared. This was an upward movement by 1. And then we said, okay, what about transformations when the value being added or subtracted is being squared? We said this one is a little bit trickier. We have to ask what value would make this 0. X equals 3 makes that 0, and so this is a movement to the right by 3. So we want to look at, how do I graph these? Well, if I start with my basic shape, and then we move up by 1, I would expect my vertex for f of x to be there. So let's look. X, f of x, -2, -1, 0, 1, 2. -2 squared plus 1, 4 plus 1 is 5. -1 squared plus 1, 1 plus 1 is 2. 0 squared plus 1 is 1. 1 squared plus 1 is 2. 2 squared plus 1 is 5. So we have 1, 2, 3, 4, 5. This is f of x. And then we have the one that moves to the right by 3, and this is actually going to have a different table. I'm not going to use -2, -1, 0, 1, and 2, because remember in example 2, we had to keep extending our table. So instead, we're going to use this knowledge that it's moved to the right by 3 to say, let me center my table at 3. So instead of centering my table at 0, I'm centering my table at 3. So then I'm going to go less by 2, 2, 1, and more by 2, 4, 5. Now, why did I choose to do that? Because my parabola has been shifted over, if I chose to start at -2, I'm going to end up with very large values. And so I'm choosing the 5 values to plot points around where I know my vertex will be. So remember, we said we want to have values on both sides of the parabola, and that's what this will help us with. So what happens when x is 1? G of x is 1 minus 3 squared. -2 squared is 4. 2 minus 3 squared. 2 minus 3 is -1. Squared is 1. Notice these are the same values that we saw in example 2. 3 minus 3 squared is 0. 4 minus 3 is 1. Squared is 1. 5 minus 3 is 2. Squared is 4. So now we have over by 3. And there are our points. G of x. Now I'm going to use a different color to graph this last one, h of x, so that you can see what's happening. So for h of x, we are not only going up by 1, but also right by 3. Okay, so when I find my points, I want to start my table at 3 because that's where my middle will be. So we have x and h of x. We'll use 1, 2, 3, 4, and 5 again. So when x is 1, h of x is 1 minus 3 squared plus 1. 1 minus 3 is negative 2. Squared is 4. 4 plus 1 is 5. 2 minus 3 squared plus 1 equals 2 minus 3 is negative 1. Squared is a positive 1. Plus 1 is 2. Now, if you're following along on your table from g of x, notice we're taking these values and we're just adding 1 to them. This is the same calculation, and then we have to add 1. So we're finding g of x plus 1, really. For 3, we have 3 minus 3 squared, which is 0, plus 1 is 1. 4 minus 3 is 1, squared is 1, plus 1 is 2. And 5 minus 3 is 2, squared is 4, plus 1 is 5. So what are our points? We have here 3, 1, 2, 2, and 4, 2. 1, 5, 1, 5, and 5, 5. Why did I do them in that order? Well, I started at the vertex and I made my way up both sides. So that kind of shows you the symmetry. So what is the difference here between h of x and g of x? We've really just moved everything up by 1. Between f of x and h of x, we moved everything over by 3. So we did both. We moved up 1 and right by 3 from our original graph of x squared. Let's take a look at the next page. If we can move sideways and we can move up and down, what about if we need to change the actual shape of the parabola? So in example 4, we're looking at, again, comparing a few different quadratic equations to see what happens when I, instead of adding and subtracting, what happens when I multiply? So I'm going to switch back to my pencil, and we will choose just our basic starting points. So if I'm looking at all of these squared values, what would make all of those 0 is the value of 0. So that's going to be my middle value is 0, negative 1, negative 2, 1, and 2. So again, we're going to start by looking at our basic, our x squared values, our parent function. Again, this is called a parent function. So when I take negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. There's my basic parent function for x squared. Okay, and I'm actually going to use 2 colors here. I'll use purple for the g of x for 3x squared. So we're going to take x squared and now we're going to multiply those values by 3. So we're taking 3 times my f of x column, because f of x is that x squared value. So 3 times 4 is 12. 3 times 1 is 3. 0 times 3 is 0. 1 times 3 is 1. And 4 times 3 is 12. If we substitute negative 2 in for x, we would have negative 2 squared, which is our 4, times 3, which is our 12. So that's how we could just take this column and multiply it by 3. Because this column here, x squared, is just this first part of our function. So when we graph this, again, we have 0, 0. Then we have 1, 3, and negative 1, 3. Oops, that should be a 3. Then we have 2, 12, which is a little bit off of our graph, negative 2, 12. Now, why did we choose to graph that 12 instead of choosing just different values to graph? If we chose different values to graph, we would either have to graph fractional values of x, so we'd have to graph like half, or we would have to graph decimal values of x, so something like 0.5 or 0.3. So I chose to graph integer functions values of x and then go a little bit off of the grid that we had rather than graphing by fractions. Let's take a look at h of x, and then we'll talk about how are these all related. So h of x is 1/2 times x squared. So again, that x squared is my f of x values. I'm actually going to switch to a different color here. Blue. So this is 1/2 times f of x. So I'm going to take my f of x values and multiply them by 1/2. So 4 times 1/2 is 2. 1 times 1/2 is 1/2. 0 times 1/2 is 0. 1 times 1/2 is 1/2. And 4 times 1/2 is 2. Okay, so here I have fractions. We have a choice. We can either choose different values of x or graph these fractions. So for the comparison between these three graphs, I'm going to choose to graph the fractions. But again, it's a choice that I'm making. So again, we have 0, 0. We have 1 and negative 1, 1/2. 2 and negative 2, 2. So this graph is something like this. Here's h of x. Here's f of x. And here is g of x. So what has happened? What did this coefficient, the 3 and the 1/2, what did they do? Well, 3 took f of x and it stretched it to be 3 times taller. So this is 3 times taller. In this one, we have half, and it took f of x and it shortened it to half the size. So this is half as tall. Okay. Another way to describe this is I could say I took this parabola, and if we just look at the part in between, if we just look here at the part of the same height, the purple one looks thinner. So we can also describe this as narrower. And the blue one, looking at just to the same height, looks wider. So we can also describe this as wider. Okay, so what does the a value do? It stretches. What would the graph of 7x squared look like? Well, here we don't have any addition or subtraction. We're looking at the multiplication. If I multiplied it by 7, this would look very narrow, or we could describe it as 7 times taller. So what I'd like you to do is do the try this, and keep in mind you get to choose your x values. So this is one that you might want to choose your x values a little bit more carefully than just the -2, -1, 0, 1, 2. Otherwise, you might end up graphing some very small fractions. And then I'd like you to describe in words on Edpuzzle what is the transformation? What happened to this graph? compared to the parent function. All right, let's take a look at example 5. What is different about this example than the previous examples that we've done? When we're looking at this, there's nothing added or subtracted to the x or outside of the squared, but what we're multiplying by now is a negative. So the question is, what does that negative do? Well, let's see. Here's our x, x and f of x, or y. So this is my xy table. When x is -2, -1, 0, 1, 2. So when x is -2, we have -2 times -2 squared. Order of operations, I do the -2 squared first, which is 4. 4 times -2 is -8. That's a negative value. We haven't seen those before when we were doing these. So -8. It's possible to get a negative value on these quadratic formulas. So -2 times -1 squared. -1 squared is 1, then times -2 is -2. -2 times 0 squared. 0 squared is 0, then times -2 is still 0. -2 times 1 squared. If you've been paying attention, we should already know what the value that we expect is because of the symmetry of these values. So 1 squared is 1 times -2 is -2, and they match. So that makes us happy. -2 times 2 squared, and we're already expecting our value to be -8, but we should do the computation just to check. 2 times 2, or 2 squared rather, is 4 times -2 is -8. So here we go with the points. We start with 0, 0, and that, remember, is called our vertex. Then we have -1, -2, and 1, -2. -2, -8, and 2, -8. So what happened? Well, we had a parabola. Our standard parabola looks something like this, right? There's x squared. So what happened is it actually got stretched out. That's what the 2 does. It stretched everything by 2. I'm demonstrating. This is what the stretch by 2 would look like. But then it also flipped upside down. So the -2x squared, the 2 stretch, narrow, 2 times taller. We can describe it all 3 of those ways. The negative flips. It flips the graph upside down. Now notice it's the f of x value that's negative, not x itself. The negative is outside of the part that gets squared. Okay, so it's the y value that flips. It reflects over the x-axis, giving us negative y values because the negative is outside of the part that's actually being squared. So let's look at example 6. Example 6 is putting a lot of these together. Okay, so we're putting together the transformations, the movements, and the stretching. And we want to describe what these all mean. So the +5, outside of the parentheses, it's not being squared, means up by 5. -3, inside of the parentheses, we have to ask ourselves, what would make that 0? X would be 3 to make that 0, so this is right by 3. And then the 1/2 on the outside, this is like squishing it to be 1/2 as tall or making it wider. So we can call this a 1/2 as tall. We can also call that a compression or a squish. Or we can say that this is wider. Okay, so we need to find some points. X, f of x. The first thing we have to look at is, where's my center? My center went to the right by 3. So my middle should be 3, 2, 1, 4, 5. Okay, so there's my center. And then I'm going to start doing these computations. So 1 minus 3 squared is -2 squared, which is 4, divided by 2, because that's what the multiplying by 1/2 does. So 4 divided by 2 is 2, plus 5 equals 7. So 1, 7. Oop, that's not 1. 1, 7. And then 2 minus 3, -1 squared is 1, divided by 2 is 1/2, plus 5 is 5.5. So we're going to go to 5.5. 3 minus 3 is 0, squared is 0, divided by 2 is 0, plus 5 is 5. 4, because of the symmetry, we already know is 5.5. And 5, because of the symmetry, we already know is 7. So here's our graph. Okay, now if we're looking at this graph and we want to know how many solutions would this equation have? Well, the solutions, remember, are when we set this equal to 0. Okay, so if I were to set this equal to 0 equals 1/2 x minus 3 squared plus 5, this is the same as saying, when does y equal 0? Well, looking at this parabola, will it ever equal 0? They go up on the right, or on the left, and up on the right. So this will never cross our x-axis, or the y value will never be 0. So this has no real solutions. And if we have no real solutions, that means we have 2 complex, non-real solutions. All right, on the next page, I'd like you to try this and then describe in words what transformations, what movements are happening with this graph. So just like we did in the last example, we had 3 movements, right? In the last example, we said it moved to the right by 3, up by 5, and was half as tall. And I want you to describe this graph in that same way. And then, when you finish the try this on Edpuzzle, I'd like you to do the concept check. The concept check checks the same kind of concepts. It's checking kind of the transformations. Where is the vertex? Remember, we talked about the vertex and we talked about transformations. Can you put those together and describe to me where the vertex is? In our last example, in example 6, the vertex was the point 3, 5. So you can use that to describe where is the vertex for this concept check example. Okay, and then once you finish the concept check, there's just kind of a summary, graphing a quadratic function, a lot of the things that we talked about, okay? Particularly, I'd like you to take note, here we go, take note that the line, remember we said there's symmetry on the left side and the right side. The line that cuts in half where the symmetry is called the axis of symmetry. And we'll always have this equation x equals h, meaning it will always go through the vertex, okay? So we use this general form for the graph of a quadratic equation. H is going to be described as our horizontal movement or shift. K is described as our vertical movement or shift. A is going to be our stretch. Okay, and then our axis of symmetry always goes directly through the vertex, and that is through the line x equals h. So this is kind of summary of all of the things that we graphed. Okay, again, if you have any questions, you can reach out to me by email or on Blackbaud through the Google form as well. Okay, go ahead and conclude with a sentence on Edpuzzle.